So this is the first video dealing with a very common component of thermochemistry, and that is this notion of something called Hess's law. And so we're going to deal with three different permutations of Hess's law. So why don't we get started now? Let's look at the first one. So what we have to consider before we can look at actually Hess's law is this this diagram, because this is a pretty good analogy. So we have two hikers who are going to hike down a hill. So we have this first hiker here with the red line, and so if you watch his pathway, that's a fairly circuitous route. Oh, he's going uphill here around that sort of bluff, and then back down, back around, and so that's a pretty long route. So certainly he covered a lot of distance. But again, in terms of the actual height change, it's a fixed change in height from top to bottom. If we look at the second person, so that's the blue line, I'm going to highlight with green, that's a lot more direct. So in terms of the distance traveled, it's less. He didn't hike as far, or she didn't hike as far, but still in terms of the displacement, in terms of how far they went straight down, they went the same distance. So this kind of illustrates Hess's law. In terms of the change, we can look at this in terms of energy. In terms of the change in gravitational potential energy, there is no difference. Both of those hikers experienced the same change in gravitational potential energy. So Hess's law, now I'll just give you a text alert here. There's a lot of text coming up, so get ready to pause it if you want to copy some of it down, but I'll explain it. So essentially Hess's law, in terms of definition, looks like this. So when reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. And if we go back to our analogy, basically you could look at that long circuitous route where they actually went back uphill and around and about as a series of different reactions, but the overall reaction from the top to the bottom, that overall process is the same. The person who went essentially straight down, that's the one-step process. So we can break down a reaction of interest. This is very commonly done in chemistry. You can break down a reaction of interest into a series of simpler or easier to accomplish reactions. And you can measure delta H's, and you can calculate then a delta H for an overall equation from those series of equations. So as I said, there's three different permutations of Hess's law. We're going to look at this first one today, combining reactions, chemical reactions, algebraically. And we'll look at a couple others in the next videos. That's using what's something called the standard enthalpy of formation, and we'll use bond energies. So let's get on to this first one, combining reactions algebraically. This is known as Hess's law of heat summation. And so this little diagram, I think, illustrates this nicely. We look at this enthalpy diagram. We actually have two reactions shown in this enthalpy diagram. So this first reaction, which has a delta H value here, this first reaction is basically the combustion of carbon. Carbon solid plus oxygen yields carbon dioxide plus a half O2 gas. So complete combustion, that's a reaction. We can measure a delta H for that. The second reaction then is the combination or reaction of carbon monoxide plus oxygen yield carbon dioxide, and we have another delta H value. So that's a synthesis reaction. And so if we look at that, not surprisingly, we can perhaps view that as a single reaction as well. And there is the single reaction. So the single reaction is carbon solid plus O2 gas yielding CO2 gas. So a one-step process instead of a two-step process. And we should be able to measure or determine a delta H for that, and we can, in fact. If we look at these two values, arrow going down, arrow going from that endpoint down, what if we added those two values? We're going to get a value of negative 393.5 kilojoules. So we've added summation, heat summation. What we've done is we've added those two delta H's for those two different reactions. And the addition of those delta H just gives us the delta H for this overall equation. So in a nutshell, that's Hess's law of heat summation. Let's look at another example here, and again, you'll see kind of how it works. Two reactions. Methane plus oxygen yields carbon dioxide gas plus water vapor. And so there's a delta H for that. This is delta H2 in this case. We have another reaction. Methane plus oxygen yields carbon dioxide plus water vapor. Notice the difference. This is, liquid water. This is H2O liquid. And there's a different delta H. Makes sense. They're different reactions. The delta H should not be the same. So what do you think happens at delta H3? What's going on here? This is delta H3. Well, what's going on there is a reaction that takes water vapor, so that's H2O gas, and yields water liquid, so the liquid state. So it's a change of state, and it's change of state for a high energy state to a low energy state. Makes sense that delta H is negative, and so delta H is in fact negative, and we can determine that algebraically. We've kind of shown it here as heat summation. Negative 802 plus negative 88 yields negative 890. Makes sense. Single step, negative 890. Two steps, same value. Well, how can we show that from an algebraic point of view? So this is the second part of Hess's law of heat summation. Basically what you look for is you look for a target equation. And you're often given these, have to be given that typically. So that's, again, what we're looking for. We're trying to determine the delta H for the condensation of water from a gas to a liquid. So that's our target equation. And here are two given equations. Now, just to point out, they look very similar, but there is a difference, and that difference is shown in color here. We have one product being water liquid, and we have another product being water vapor, water gas. And so we have to manipulate these equations so that we can generate our target equation. Well, you notice everything else is the same, so all we have to do is really concentrate on the water. And so in this target equation, H2O liquid is a product. Well, here's H2O liquid as a product, so we wouldn't want to change this equation. H2O gas, on the other hand, is a reactant in our target equation. Well, here, H2O gas is a product, so this is the one we're going to manipulate. So what we want to do is reverse this equation. And if we reverse that equation, what do we get? Well, there's the reversing of that equation. So now I have the gas on as a reactant. So let's just get rid of this. We're not going to consider this anymore. But what else have I reversed? So I've reversed the equation. Now I have CO2 on the left. There's my water vapor as a reactant. I've changed the sign. This is critically important. If you reverse an equation, you've basically said, I'm deriving the reaction in the opposite way. That's going to change the enthalpy of that reaction. So now it's plus 802. And so now I can simply analyze the equation, collect like terms. So methane gas as a reactant, methane gas as a product. There is no methane gas at the end of the day. O2 gas and O2 gas. There is no O2 gas at the end of it all. Carbon dioxide and carbon dioxide, they go out. Makes sense. And there's one of my remaining compounds and the other one. So I simplify. So I simply have H2O vapor yields H2O liquid. And that's what I wanted to find. It's the same as my target equation. Delta H3 equals, so I now add these two numbers, minus 890 plus 802 equals minus 88 kilojoules. And so there's the delta H for that process, for the condensation of water, as determined by manipulating two different reactions, two different processes. So another heavy text alert. If you get a chance, you might want to pause it and copy some of this down. But it's generally just how you sort out these problems. You need to identify how the given equations need to be manipulated to yield your target. So that's just put your pencil down, have a look. Identify things as reactants in the target and where they are in your given equations. If equations are reversed, the sign of the delta H is also reversed. That's very important to remember. If the equations are multiplied by a certain coefficient, the delta H is multiplied by the same coefficient. And formulas for both sides must be the same substance, identical physical state. So this is what we saw before. Liquid water and liquid water. Those would cancel out, but H2O liquid and H2O gas are not the same. It's different physical states, so they would not cancel out. And again, it's called Hess's law of heat summation. Add together the equations to obtain your target and add delta H's. And you get a delta H for that target equation. Basically, Hess's law is about analysis and manipulation of the equations in delta H's. You have to be careful, and you have to be deliberate, and you have to be careful some more. Let's just look at this last example. So household cleaners can be mixed, and they can yield quite a toxic brew potentially. Hydrochloric acid can react with oxygen and chlorine gas, which is potentially pretty dangerous. So this is our target equation. And so what we're looking for is a delta H for this equation. Determine the enthalpy change for this reaction using the given thermochemical equations. So again, now it's about analysis and manipulation. So I look at equation 1. There's hydrogen, chlorine, HCl. Well, HCl is important. It's the only equation that contains HCl, and HCl is in our target. Here it is a reactant, and we have 4 moles of it. Here it is as a product, and we have 2 moles of it. So we're going to reverse this equation, and we're going to multiply by 2. And so let's rewrite that as 4HCl gas yields 2H2 gas plus 2Cl2 gas. And so delta H also gets reversed and multiplied by 2. When I multiply that by 2, I get plus 370 and reversed. So notice the sign gets reversed. So that's that one. So now what I do is I just get rid of it. I've manipulated that equation. I don't want to draw my attention back to it. I look at this second equation. 2H2O liquid yields 2H2 gas plus O2 gas. And the only place I have H2O in my equations is a product, but it's H2O gas. But what I do have is O2 as a reactant in my target, and this is the only place I have O2, and it's a product. So I'm going to have to reverse this, but I'm not going to have to multiply it by anything. And that should get rid of my O2 nicely. So 2H2 gas plus O2 gas yields 2H2O liquid. And so delta H gets reversed, because all I did was reverse this equation. Now it's negative 578.16 kilojoules. And so again, I've changed that equation, so I'm just going to get rid of it, so I don't go back to that one. Finally, H2O gas and H2O liquid. Okay, so in this case, we're trying to deal with water. And again, I have vapor as a product in my reaction. So I'm going to reverse that equation, and I'm going to multiply by 2 again. And so that becomes 2H2O liquid yields 2H2O gas. And the delta H sign is going to change, and the magnitude is going to change, and that becomes plus 81.4 kilojoules. And so again, I've manipulated that equation. So now I'm ready to add everything together. I'm ready for the summation business. So let's just identify what I want at the end. Well, 4HCl, there's my 4HCl, so that's good. H2 gas should be gone. 2H2 gas is gone. O2 should be gone. Or sorry, O should be remaining. Cl2 should be remaining. There it is, 2 moles of Cl2. H2O liquid. So they cancel out. Same physical state. So there I have everything I need, so I can rewrite that. 4HCl gas plus O2 gas yields 2Cl2 gas plus 2H2O gas. Delta H of the reaction equals, and I add everything together, and when I add it together I get negative 120 kilojoules. So that, in a nutshell, is Hess's law. And so like I said, you have to analyze things, you have to think about it a little bit, you have to manipulate appropriately, and remember, get everything ready so you can add it back together. Once you're ready to add, it becomes pretty straightforward. And that concludes this video.